Welcome to our tour of EMS's Microelectronics area, a collection of outstanding people, products, and equipment in a state-of-the-art facility. EMS Microelectronics supports many projects with quality service on a variety of hardware, from microwave to low frequency, from high power to low loss. We support space, military, and commercial programs. Our people and facilities have the technology for you, from thin film through advanced integration. Now join us on a tour of the magic and the amazing as we go inside microelectronics.
Hi, I'm Keith Washington, and this is Margaret Cash.
Hi.
We're going to be your host today on a guide through our microelectronics facility. We began microelectronics operations back in 1982 over in Building 125 Technology Park. Horton Prather was the first in this new operation, which gave us in-house capability to build hybrid microcircuits, solid-state components, and microwave subsystems.
The whole idea is to make things smaller, reduce the size and weight of our hardware through microelectronics integration. Let us show you what we mean. Here's a typical circuit board used in one of our products. Now look at a hybrid microcircuit, which does the same thing. The result is a 10-to-1 reduction in size and weight.
Nice. Show us how they do that.
Well, they place the board on a table and stand 5 to 10 feet away and telepathically crush it between their fingers, like this. I crush you. I crush. Crush, crush.
No. Too much.
Oh.
Back off. There, that's it.
Wow, thanks. But maybe we should show them the other way to do this.
You're right. EMS does have over 7,000 square feet of clean room space and 20 people working in our microelectronics facility. We enter here through these doors into the gowning area.
We have several rules and specialized requirements for working in the clean room to keep the work area and the hardware clean.
We use lab coats that are clean room only, not to be worn in other parts of the facility. Tacky mats, bouffant caps to keep dust and airborne particles to a minimum. And to tell us about some of these is our lab supervisor, Randy Bunn.
Hi. Notice that I'm wearing a blue coat. White coats are for our customers only.
Randy, can you tell us a little about your tacky mat?
Sure, Margaret. As you can see, we use a high-tension adhesive that will keep the debris off your shoes and you won't drag it into the facility.
Does anything ever get trapped on there?
Yes, occasionally we have technicians who get stuck and we have to free them before they're devoured by functional or program managers.
I know it's not a pretty sight. What about these bouffant caps? Is there any interesting ways that people are wearing these days?
Yeah, sure. There's the beret style that's very popular. And there's also the cone head hat that's catching on. And then there's also now the bouquet of bouffant style that's also popular.
Wow, no wonder we got 1772 certified.
You know that we are only one of 4 companies in the world that have Class H and Class K certification, and we have the ability to build fully compliant space and military hybrids.
That's great. We use the term hybrid microcircuit to describe microelectronics assemblies which integrate multiple chip components on a printed substrate.
Here's a display showing several examples of EMS-built hybrids for microwave and low-frequency applications.
The basic printed substrate that we use is a metal-coated ceramic-based material that's fabricated here at EMS using thin film technology. I'd like to introduce Richard Plack, a technician here in our microelectronics area.
Hi.
Richard, what can you tell us about the sputtering system?
Well, it's probably the most complex system in the facility. It has computer controls, high power RF and DC, pneumatic and hydraulic components, high vacuum system with 2 cryo pumps and moving mechanical parts. Our system is a 3-target RF and DC magnetron system capable of depositing films from a few angstroms to several microns thick.
Wow, you mean like in the metric system?
Wow, check out the big brain on Keith. Yeah, the metric system. Like this slide has about 200 angstrom of chromium metal, which is nearly transparent when held up to the light.
Right, and the system is highly automated and has the ability to process thousands of parts per week with tremendous accuracy and consistency. This is a copper sputter target. It's the source of the metal in the process.
Thanks, Richard. What else have we got?
This is our electroplating line. When combined with sputtering, we can create a wide range of thicknesses and layers.
Combinations of copper, nickel, and gold are used on substrates like this.
Okay, well let's move on to the yellow room.
What yellow? Looks like normal light to me.
Oh, you. I'll crush your head and make you see yellow.
Hold on. We've got yellow light in here because the process used to make substrates is light sensitive.
Okay, this is a type of photographic darkroom. How about showing us this machine?
This is our dicing saw. This machine can be used to cut grooves or cut through ceramic substrates of all shapes and sizes using optical alignment and high-speed air-bearing spindle. We can also support our substrate fabrication process with a low-power YAG laser for scribing, marking, and cutting in some applications. This window is a safety device that allows the operator to see in the laser without harmful effects to the operator.
Among our technicians working in this area is Conover Jones. Hi, CJ.
Hi, Margaret.
What are you working on today?
We are analyzing the coating thickness using X-rays. This machine can tell us the thickness as well as the chemical composition of a metal coating.
Another yellow room technician is Jerry Mize.
Hi, Margaret.
What you doing, Jerry?
I'm coating substrates with photoresist to make the etching pattern.
Cool, looks like spin art. Look what I made.
Let's move on. Here's an example of a substrate in process. This piece is 2 by 2 inches. The finished part will have over 50 integrated film resistors and later will be assembled into a J-Stars driver hybrid.
Next we have Rita Burrell performing die attach. We have equipment here at EMS to perform either high temperature solder of chip components or silver conductive epoxy.
This is the machine we bond our high-powered parts with.
Okay, first we pick up the die. Then we move over to the part. We place the preform, move the preform tool out of the way, and place the die. Just like that.
With the epoxy machine, we can place up to 100 parts per hour into this J-Stars hybrid. This hybrid for the Milstar program is our latest Class K hybrid microcircuit. Note the chip components and wire bonds. Each wire is smaller than a human hair. Next, on the automatic wire bonder, we have Thong Lee.
The wire used in this bonding operation is about 1/3 the diameter of your hair. What hybrid are you working on now, Lee?
I'm programming a new hybrid for our space power converter.
And do you run the machine for us?
Sure.
The machine puts down about 1 wire every second. Here we're going to bond a hybrid assembly with about 70 wires. He's going to go through video imaging to precisely align the device before bonding. We've slowed the machine down to about 1/3 its normal speed for the purposes of the demonstration. The wire is a high purity gold wire that's fed down through a ceramic capillary, sort of like a sewing machine, and we have a ball that's formed on the end of the capillary that's then compressed down into the surface of the die components to form the wire bond.
Now to tell us about the belt furnace and sealing operation is Mike Carter.
Our final sealing of a hybrid can be performed 2 ways. One way, if the lid is to be soldered on, we have this atmosphere-controlled furnace. Or for lids that are welded on, we have the seam sealer over here.
Our seam seal operator is Mr. Robert Morris. The seam sealer is another piece of automated equipment that's controlled by a computer and has high volume capability and a robot mechanism that seals and welds the hybrid lids to the hybrid cases. Electrodes sense the height of the device being welded, pressure is applied, and then current across the two electrodes welds the hybrid lid in the package. The lid and the package are kept cool by sitting in a heat sink fixture, so the hybrid never gets above about 50 degrees. After sealing, the hybrid goes through our screening process, which we call shake, rattle, and roll, which includes X-ray, temperature cycling, burn-in, constant acceleration, and particle impact noise detection.
Gene Hall is responsible for much of our automated hybrid testing.
This is our manual probe station we use in testing our hybrids. This is our automated test setup, which we test our hybrids in. Usually it takes very many weeks to do our testing on our hybrids. Here we have 70 hybrids we're fixing to start on a 2-week burn-in.
The next stop on our tour is our solder assembly area. In the solder assembly area, we don't wear the bouffant caps because we don't do open chip and wire assembly as we do in the hybrid area. We do mainly soldering technology. The supervisor in our solder assembly area is Irene Good.
Hey. Solder assembly is where we built programs such as the UHF follow-on, Telstar up converters, IA down converters and up converters, DLA EchoStar, and many other solid-state power amplifier projects.
Sherry Walls is here to show us some of our latest power monitors. Sherry.
Yes.
Seems that people in here really approve of our new radio policy. Sherry, what are you working on?
This is a 20-watt KU band amplifier for space station. It is a balanced design with an airline divider and combiner to a waveguide output. The subsystem also includes an EMS power converter. And this is our 40-watt X-band power amp with chip and wire amp stages. This is our smallest and highest power module to date.
This technology will also be implemented on our Mars 98 program, which goes into production later this year. Sorry to interrupt, Sherry.
We also have some of our global positioning system satellite hardware.
This hardware uses the latest in materials and packaging for space subsystem technology. EMS hopes to build this hardware for GPS for many years to come.
Several areas in this facility are dedicated to electrical testing of the hardware. The GPS hardware has several test stations developed by a team of engineers and technicians, including Todd Thornton.
Hi, Margaret. How are you? Look, Brett, I'm wearing my wrist strap. I'm over here tuning a power amplifier for the Sandia RFA job. I'd like to show you some of the special test equipment we designed and developed for the Sandia RFA job.
Okay.
It's over this way. Let's go.
Let's take a look.
Here's our piece of special test equipment. We've entitled it the Sandia RFA Deck Level STE. It's got our logo here, and Sandia's logo. This piece of special test equipment is capable of testing 2 transmitters, a receiver, and a power amplifier, and another unit which we aren't building here. It tests all the Vacelock loop oscillators and all the functions for each unit, applies the proper DC voltages, and measures current. And that's about it.
That's great, Todd. We'd like to hear more, but we only have 2 hours of videotape, so we better save some for the sequel.
Hi, Mom.
To complete our tour, we have our Quality Assurance Inspection Team, Dawn Franklin and Carolyn Foster.
We perform many of our inspections under laminar flow hoods, wearing face masks, since we are the last ones to look at the hardware before it is sealed.
All right. Well, show us your stamps.
Man, I wish I had one of those.
I wish you had a face mask. Anyway, that's all for today. Thanks for joining us inside microelectronics. You know, it really is a small world after all.
It's a small world after all. It's a small world after all. It's a small world after all. It's a small